Okay, let's get started then. So the topic of today's lecture is node centrality. In general, one of the big questions that people ask when they start studying networks is which vertex is really important in the network, or which vertices. And that question occurs all the time, whether you want to just study the network or even if you want to visualize the network. For example, on this beautiful picture, by just looking at it, you see that there is a bunch of nodes in the center that are probably important. Well, actually, to do this visualization, you need to be able to find those nodes and draw them appropriately. And in general, even without visualization, when you study the network, it's very important to know which node plays sort of critical role in the network. There is another question that might be asked when you study networks is, okay, well, if we have all those people in the network, is it possible to rank them, right? So there are all those nodes. There are connections. Maybe there is some particular ranking or ordering of the network where the first node is the most important and the last node will be the least important in that ranking. So in any case, one needs to come up with a notion of importance of the nodes, or centrality of the nodes, like how much a particular node is central to this network. And of course, the answer to this question really depends on what one means by importance. So we'll start this topic by actually going back to graph theory and just look at the graph-theoretical definitions of node importance, see what nodes are important in that sense. Graph theory really deals with the notion of the centrality of the nodes. So first of all, the definition. And I mean, the good news about graph theory is the definitions are very short and precise, and there is no ambiguity in understanding them. You will notice that later on that there are other metrics and measures that come from sociology, psychology, other sciences that are, well, less ambiguous. But with the graph theory, everything is very clear. So first of all, we define the eccentricity of a vertex as a maximum distance between this vertex and any other vertex on a graph. So if you look at the picture, the numbers here, they actually tell us eccentricity values. So for example, we can look at the node number. At this node, it says eccentricity 3. Well, it means the largest distance from this node to any other node on the graph is 3. And just checking it out, the distance here is 2. The distance along this direction is 3. The distance along this branch is also 3. So the eccentricity is 3. Okay. The eccentricity is 4 for this node is because the longest path for this from this node to any other node is of the length 4. Okay. So you can define and calculate eccentricity for every node in the graph. Then from that definition, you can define, well, first of all, the well-known for us value of a graph diameter. And graph diameter is just the largest eccentricity, which makes sense because if you remember, when we talked about graph diameter, it is the largest possible distance between any two nodes in the graph. Well, and that's what it really says. Eccentricity is for one fixed node, we take the largest distance, and here we go over all the eccentricities, which means we're going over all nodes, all pairs of nodes. But there is a new definition we haven't met before, which is the radius of the graph. And the radius is a minimal eccentricity. So we have the maximum eccentricity, which is the diameter, and we have the minimum eccentricity, which is the radius of the graph. Okay, and so for example, for this graph, we have a radius equal to 2, diameter is equal to 4, right? For this graph, radius is 2, diameter is 3. Okay, so the radius, again, is the smallest eccentricity, diameter is the largest. And now the key definition for us is that the central point in the graph is the point where the eccentricity of that point is equal to the graph radius. So, for example, on the graph on the left, the radius of the graph is 2, and there is this point that has that has eccentricity 2. On this picture, there are 2 points with eccentricity 2 equal to the radius, and so they are considered to be central from graph-theoretical point of view, central to the graph. So this definition actually tells us, geometrically, if you think about the graph just in the sense of a bunch of nodes connected by a bunch of edges, well, sort of geometrically, by looking at the distances along the edges, which points are central. In fact, the definition goes further and defines graph center as a set of nodes. Well, it's a set of all central nodes, right? Or it's a set of vertices whose eccentricity is equal to the radius. And we can also define graph periphery as a set of vertices that have eccentricities equal to the graph diameter. So again, it's pretty intuitive, which means that the periphery are those nodes that are on the fringes of the graph, sort of, and the center of the graph are the nodes that are, well, sort of located in the center. Now, this is really, beautiful definition. It is actually harder to use in practice. And there are several reasons for that. Well, there is a computational reason, of course, because to calculate this, you need to calculate all the shortest path between all the nodes. But aside from that, one of the main difficulties here is, as we actually seen previously, the notion of, say, diameter, and of course radius, is very, very sensitive to small changes in the graph. Okay? So imagine that you take any of these graphs and we add just one more node somewhere here, and all of a sudden all the numbers will change, and the center will change, and radius, diameter will change. And on the other hand, even if you take like this, say, very small and very compact graph shown here, and for example add a chain of nodes, the diameter of the graph will increase dramatically. Though we realize that probably when we talk about the graph and compactness, this graph is still pretty small because most of the nodes are right there. So one can use these definitions, but have to be careful with them, and don't be surprised if by any small changes they change dramatically. And again, since most of the graphs that we're going to be dealing with, or networks, they actually come from experiments and from measurements, well, measurements contain noise. And that's why the susceptibility of the metric to small changes is sort of a bad feature in this case. Well, but the good news, the definition is very clean, and it's very unambiguous. So it's very clear which nodes are actually called center, which called periphery. Now, later on in the lecture, in today's lecture, and in the papers, you will see quite often people talking about, say, the center of the graph, or the core of the graph, and that periphery. And they use the word periphery in the looser sense. So they actually think about periphery as, yes, as those nodes that are on the periphery of the graph, but they're not using it in the sense of graph theoretical definition. So again, if you want to use a very precise notation, here's the definition of what periphery is for the graph. Periphery are those nodes that have eccentricities equal to the graph diameter. But in sort of usual meaning, periphery is those nodes that are far away from the center of the graph. Right? Just think about, I don't know, Moscow subway, and you realize which stations are the periphery, right, and which are in the center. So that's a take on nodes' importance from the graph theoretical perspective. But there is actually much more work has been done on the notion of nodes' importance, or vertices importance, from the point of view of sociology. And the reason for that is because there is a clear association in between the location, the position of the actor of the node in the social graph and its power. And again, there are many ways to define power. Power can be in terms of that you can propagate information. The power can be in the sense that you can influence other people, and many other sort of shades of power. But the point is that the location of the actor in the network, its connection, is tightly related to the power that this person has, or the actor has within the network. And that's why this topic has been in the center of sociological research for a very long time. Now, here I just give a reference for Linton Freeman paper 1979. It's just because in that paper he gave very good overview of the measures of centrality for the actors. But in fact, a lot of work goes on the centrality goes to 30s. And today we're going to talk about those metrics and how they differ and what they actually measure. So there are a couple things, again, a couple sort of some terminology that we need to know. Well, first of all, this is centrality. When somebody talks about centrality, and in particular in a social network, it's really the question of involvement with other people, other actors in the network, the ties in the network, the fact that messages going through that person. And typically, centrality refers to undirected network. So when somebody talks about friendship, well, we define, centrality for that network, of friends. So interaction between actors in that network is symmetric. But of course, that notion can be extended to directed network. And sort of originally, when somebody talks about directed network and corresponding metrics, they talk about prestige. And prestige really means how many ties or how many edges or links an object or person, an actor receives from surrounding actors. So, if you think about scientific paper, it's how many citations it got. So that's going to be a prestige of the paper. So those definitions make sense. Now, again, one sort of important note here is that if we compare to graph theoretical definitions, that is very unambiguous. Here, quite often people talking about centrality for directed networks, and well, you will see that in the formulas. Again, originally there was this notion of centrality and prestige. Now there are a lot of things that are kind of mixed up. But again, the tradition is that prestige usually means in a directed network when the node receives a lot of sort of attention in the sense of the incoming links. Now, whatever the centrality measures or metrics we can come up, there are some very, very simple graphs, and here are those graphs for which the centrality metrics are kind of obvious, and whatever centrality metric we can come up with, they should sort of make sense for those networks. Let's take a look. Well, for example, it's very clear that on the network on the left, on this one, there is a big difference in between nodes in terms of their centrality, in terms of their importance to the network. It's very clear that whatever centrality metric we choose, node A has to be the most central. Well, because it's geometrically is the most central. It has most of the connections if we define the centrality as a number of connections the node has. You probably already talked at the seminar about the closeness metrics and the betweenness metrics, and if you look at this picture, you realize that yes, all the shortest paths between every pair of nodes here go through node A. So node A has to be the most central node in this network. At the same time, if we look at this picture, it's also clear that all nodes has to be equivalent. It's very symmetric in term for every node, and so whatever centrality measure metric we can come up with for this graph, every node should be equal. And the last graph, which is a line, again, just intuitively, it's very clear that the nodes here will probably be more central than these nodes, and definitely much more central than those nodes. So this is just sort of three test graphs, and whenever you build or code centrality metric, or invent a centrality metric, it should behave reasonably on those graphs. And actually, these graphs are very good test cases to compute on, because it's the answer is sort of obvious for them. All right. So let's move on and actually look at some definitions. So first of all, the obvious centrality metric is degree centrality, which is really just the number of the nearest neighbors of the node. So it's not degree; it's sort of nothing else, and that's why I equate it to Ki. And we're going to be talking again. We're talking about centrality. So today we'll be mostly talking about undirected networks. So the undirected network has a symmetric adjacency matrix, and so the node degree we can actually calculate by looking at the matrix either as a sum of every element in the row or as a sum of every element in the column. Okay. Now, though the node centrality by itself is quite convenient metric, but it is absolute metrics in the sense that you cannot really compare centrality of the nodes that belong to two different graphs. And the reason for that is because the one graph can be much denser than other graph, and on average, nodes in that graph will have high centrality. So if you all of a sudden want to compare nodes across graphs, you would rather want to have something more of a normalized centrality. And again, the notion for this is because, let's say you want to compare the structure of two different organizations, and they have, for example, a different number of people and different number of nodes, and you want to compare the centrality of the people in the organization. If the one organization has sort of stronger express centrality is more centralized than the other, well, to do that comparison, you need relative metrics for centrality. And it's very easy to do. In fact, the idea is the following. To calculate the normalized centrality, we can think of the measurements of the centrality for the graph that we know has the maximal possible centrality. And we do know that, well, the star graph has the maximum possible centrality for the central node. And so we can normalize centrality. We can normalize centrality to that value. So to the centrality of the node in the star configuration. But this graph, has, for the graph that has the same number of nodes as your graph. And so if you think about it, let's say you have n nodes in the graph, then the central node will have n minus 1 neighbors. And if it has n minus 1 neighbors, the maximal possible degree for the star type of a network, for the central node in the star type network, will be n minus 1. And so if we want to come up with a normalized degree metric, well, we'll just take our degree centrality for every node and just divide it by n minus 1. And then it guaranteed that even if our network is sort of this star, which is the most centrally optimized network, then the centrality measure for the node will be 1 or close to 1. And then we can easily, without even knowing the size of the graph, if you give a number that tells you centrality metric, you can tell, okay, how central that node is. Without normalization, if I tell you the centrality measure for the node is 659, well, it really doesn't tell you a lot. But if I tell you normalized degree centrality, which will be, say, 0.97, well, you realize that this node is very, very centrally located in the sense of the degree. So it actually collects most of the degree, or most of the edges in the graph. Okay, so that's degree centrality. This is the simplest metric of centrality. In fact, it's very useful, and it's very easy to compute. It is local. It really does not take into account the structure of the graph. To compute this metric, you just really care about nearest neighbors. And that information is usually easily accessible, and you can easily compute this one. Another metric, this metric goes back historically to 1940s, 1980s. I'm sorry, 1940s, 1950s. Actually introduced by the psychologist Alex Betweenness, who studied interaction in an organization, a group of people. And the idea here is actually calculate how close, on average, a node is to any other node in the system. And closeness is defined in terms of the shortest path. So for every node, you take and you calculate the distance from this node to every other node in the network. And then you take 1 over that value. And so it's clear that for the nodes that are sort of central, that have the smallest total sum of the distances from this node to every other node, well, the inverse of that will be the largest value. It is somewhat similar to the notion of the radius of the graph and the central node from graph-theoretic point of view. Just take a look at it. But it is much, much more stable because it doesn't have this values, that doesn't have minima, or it doesn't take the smallest or the largest value, right? So it's not that sensitive to addition of one more node to the network or small changes in the network. The same way as with degree centrality, closeness centrality also can be normalized. And again, we just compare it against the star network. And when doing the star network, the central node, again, has n minus 1 nearest neighbors. And so the total sum of all the distances from this node to all its neighbors will be, in this case, n-1, right? Because one for every edge. And so n-1 edges, so it's going to be n-1. But now, since it goes into denominator, to normalize it to be a metric sort of in between 0 and 1, we need to multiply it by n-1 instead of dividing. Okay, and so as a result, this is a normalized closed centrality. So this one is much more of sort of geometric centrality of the graph, and it's clear that the actor was a node that is that has high closeness centrality. It has shortest communication paths or shortest distances to all other nodes in the network. So here you can think of also already about sort of communication, or how easily it is for this node to reach other nodes, in the network. And so this centrality, is sort of more about friendship, or the friends of yours, etc., etc., etc. So about the sort of the compactness organization of the network, right? And so in this sense, this centrality already reflects the general structure of the network. Now, there are troubles with the centrality if your graph is disconnected, right? So if your graph has, for example, is a star graph, and then there is another node over there, then it's not very clear how to use this, because the distance in between any node and that node will be infinite, and then it's just gonna ruin the entire metric. So you have to be careful and calculate it only for connected components. Now, there is a remedy, and in fact, there is sort of alternative or slightly different definition of closeness centrality. It's called harmonic centrality. It came up a few years ago, and actually people using it for some research. So the idea is, if you notice, the difference here is that it's really a harmonic mean of the it's harmonic mean of the distances, right? So in the original definition, we're adding up all the distances and then taking inverse of them. In harmonic centrality, we're actually inverting each and every distance. And in this sense, if the distance between any pair of nodes is infinite, it's not a big deal in this definition, because 1 divided by infinity is 0, and so it just does not contribute to this definition. And so in practice, people started using this. But again, classical closeness centrality is given by this formula. Okay. Again, this is 1950s. That's sort of how far back this goes. Finally, I think one of the most interesting definition of the centrality is called Betweenness centrality. And here the idea is the following. And actually, in fact, it was introduced by Linton Freeman. And the idea is the following. Imagine that we're considering the message passing through the network. It's clear that certain nodes play more important roles than others. So certain nodes can serve as bridges. And here is sort of very, very clear example that the node A is actually on the path connecting two communities, two groups of nodes. And whenever any node from the red nodes wants to communicate with any other node in the blue nodes, they have to go through node A. And in this sense, node A is very, very much privileged node. And it does have lots and lots of power. And very often, a lot of people in organization, instead of producing things, they just try to position themselves in this role, sort of be indispensable in communications. And then you really cannot get rid of these people. There are some good roles and some bad roles, but this is sort of the idea. And to calculate the centrality, we need to calculate the total number of shortest path that goes through this particular node. In fact, in this picture, whenever you need to get from one side of the graph to another side, you have to go through node A. It's not always the case. You can think of, and we're talking about the shortest path. We can think of sort of the following situation for the graph. So this is node A and node B, and we're trying to calculate the centrality for this node, for node I. Well, there are actually two ways to get from node A to node B. There is this route and there is that route, and both of those routes actually have the same length. And so then the importance of node, or the centrality, the importance of this node, of node I, of course, has to be less compared to the case when this is the only way. And if there are two ways, well, let's just half it and say it's one half. And so the definition for the centrality, for the betweenness centrality, will be the following. For the node I, we calculate the total number of shortest path that goes from any node S to any node T through node I, and divided by the total number of shortest path between node S and node T. So if all the path goes through node I, then the betweenness centrality is the largest. And if some of them, like on this picture I showed, have alternatives, well, it contributes less to the betweenness centrality. Now, this is not a normalization in the sense that the larger graph will still give you large values for betweenness centrality. And again, like in the previous cases, we might want to normalize this metric to be able to compare centrality metrics between different graphs, or don't worry about the graph size. And the reason for this normalization is very simple. Again, if you have n nodes in the graph, then you should be able, n nodes on the graph, we can split in two parts, and we try to calculate the total number of shortest path that go from one group to another group through your particular node. And we again will compare this to the star metric, and there is, if we look at the star graph, let me give me a sec. So if you look at the star graph, there are n-1 ways to select, the first node from which, node S, from which to calculate, from which to start the route. There are n-2 ways to calculate, to define another node to the node to which we go. Okay, and that's why there is n-1 times n-2, and we don't want to double count. Then that's why there is 2 in numerator right now. So it will be n-1, n-2 divided by 2 ways to go through the central node in the case of a star graph, and that's a normalization. So again, in the star graph, by using this normalization, we're making sure that it normalized betweenness centrality is equal to 1 for this very central node. So these are sort of the 3 basic metrics for centrality. All comes from sociology. With probably differences in 20 years from one to another in terms of when they were introduced, and they measure different things. And in fact, all 3 of them are very useful. It really depends on what kind of question you're trying to ask, and what do you understand by importance of the node. Just be careful when reporting those numbers. Make sure that, and reading those numbers in the papers, make sure we're talking about betweenness centrality or normalized betweenness centrality, because one will be a large number, the other one will be in between 0 and 1, and that has to do with other centralities too. But there is there are other ideas that relates to centrality, and I think one of the key idea that we'll talk about, we'll talk more about this idea, and we'll use it a lot, is the following. In the very first metric, in the degree centrality, for example, we just counted the number of neighbors. Okay. Well, though it is an important metric, but we might take into account who the neighbors are. So it would make sense that an important person will have important neighbors and a connection as a connectors. So this is sort of the picture shows you with the node sizes that we can look at, say, the big node connected to other big nodes in the sense of the importance. So this definition is recursive, right? So the node is important if the node neighbors are important, right? And then you go into the node neighbor, and that node neighbor is important, if that node neighbor is important, and so on and so forth. So if we try to express that mathematically, what it means is the following. Well, the node degree or the node importance, I use this Vi as node importance, is the sum of the importance of the neighbors. So we can do it that way. The question is if there's anything wrong with this definition. Yes.
So it's basically page rank.
I'm sorry, can you repeat it?
It is basically page rank?
Well, we will actually talk about page rank next time. There are more interesting and intricate details about page rank, but the idea is there. The idea is there. It's the same type of an idea. We're right now, first of all, we talk about undirected graphs and page rank defined for directed nodes, and it's for directed graphs, and it significantly simplifies for undirected graphs. But there are other things that are very important in page rank. But we'll talk about it, next lecture will be actually devoted pretty much to page rank and other sort of web graph metrics. But here, one thing which I want to point out, how can you sort of, how can you implement this metric? One way to deal with this is like, okay, well, you know what? Let's just take all the nodes and give everyone, importance, I don't know, importance 1, and then calculate these values, okay? And then, take these values, and now they will be different from 1 because for every node has different number of neighbors. And take these values and plug it back there, calculate it again, and just keep going. Do you guys see any problems with this type of iterations? Just if you try to do this, what's going to happen with the values Vi? Well, I can tell absolute values Vi if you wish to. Aij is positive, so it's always positive, but I'm interested in the size of Vi's. If you keep going that way, Vi's will be growing. Well, simply because in every iteration, the only thing you do is you multiply this Vi's by the adjacency matrix that has the content of the matrix are integers that tells you about how many nodes connected to this node. So you multiply by some integer. Well, can be equal to 1 or greater than 1. and you add them up. And so on every iteration, the VI values will increase. And so there is no like convergence in this recursion. You will, the numbers will keep growing and growing and growing and growing. And so this process, in order to be meaningful, in order to sort of converge to some value, and that's what we expect from this process, right? That you start from some values for every node, you iterate, and then eventually, at some moment, the values will stop changing, right? There will be convergence to certain importance for every node. Well, in order for this to happen, on every iteration, we in fact have to normalize the sum, or sort of reduce the values that being propagated. And so you need to come up with some parameter, some constant, some damping factor, right? And usually defined as 1 over lambda. Well, the reason you write it that way is because, of course, when you write it that way, you instantly see that what we have here is just an equation for eigenvalues and eigenvectors. And in this sense, yes, it is similar to PageRank. It's just the matrix that's going to be used in PageRank will be different. Here, A is adjacency matrix, and in PageRank, we're going to be using what's called random walk matrix, or the probability matrix. But yeah, it's eigenvalues, eigenvectors. And then what we do is we'll select an eigenvector that is associated with the largest eigenvalue, and we'll use that eigenvector as an importance, a metric for the importance of the nodes. So, eigenvector is a vector, and it will have certain values. They're not necessarily integer values, but every node will have some value associated with that node in the graph, and that value will be the importance of the node according to eigenvector centrality. So the key here is in eigenvector centrality, it's the nodes that are connected to other. So if the node has a large centrality, if it is connected to the nodes with large centralities. So in this case, the nodes with similar centrality will sort of group together, because they need to be connected, and so you will see groups of nodes with large centrality according to this metric. So let's take a look at this. Here's an example. I think a very nice example comparing a few different centralities. So closeness centrality. When you have closeness centrality, these are the nodes, highlighted nodes, with the highest closeness centrality in the graph. And so these are nodes that within their own clusters, they're very well connected. And they have high closeness centrality because, again, if I remind you, closeness centrality is defined by as an inverse distance from the node to all other nodes, right? And so if you have a bunch of nodes that are tightly connected with you with a very short distance, distance 1, for example, that gives you a very strong boost to the centrality. And of course, the nodes from other clusters, they are, they affect your centrality less, but still, if you belong to the cluster, your centrality, in the sense, will be higher than for the nodes that are sort of not parts of the cluster, like these nodes, or like these nodes. So that's closeness centrality. The next is very, very also clean statement for betweenness centrality. There are some nodes in this picture that act as bridges. And these are those nodes. And again, these are nodes that has highest value of betweenness centrality in the graph. And you realize that if you consider, for example, the information transfer in the network, these nodes will be key players. Information goes to them. In fact, speaking about betweenness centrality, there is an extension to the notion of betweenness centrality for the nodes and to the betweenness centrality of the edges. You can also talk not only about the central node, but also about sort of central or important edges in the graph. Again, here we're talking about only about nodes, but just keep in mind that you can extend this to edges that can be bridges. So, but anyway, this is a betweenness centrality. Now, how do you think? What do you think the eigenvector centrality look like for this type of graph? Which nodes will have highest eigenvector centrality? Remember, we discussed that for eigenvector centrality, it's important that if a node is central, sort of other nodes in its closest neighborhood, well, in closest neighborhood means connected to this node, will also have high centrality, because that's the only way for a node to have high centrality. So the good proxy for this would be the idea that you look at the largest cluster, and that would be the nodes in the largest cluster. All of them will get you high centrality. Again, they have to be connected, otherwise you're not going to get high centrality, high eigenvector centrality. So if you notice, we looked at the three different centrality metrics, and they highlighted very different nodes. Sometimes for some graphs, I mean, this is sort of extreme cases. This is very well-designed example to show you the differences. Quite often, differences will not be so explicit and so easy to see. Often those centrality metrics will be quite correlated, but at the same time, these are different metrics. Okay. The search for centrality metrics hasn't stopped on those metrics, and in fact, I'm jumping here in time a little bit. This metric goes back to 1953, and this metric was proposed by Leo Katz, who was a statistician. And so you start seeing, more mathematical formulas in here. And the idea is the following for this metric. Let's take into account not only, the direct connections, the shortest sort of the direct neighborhood, but also the influence from the next nearest nodes, and next nearest nodes, and next nearest nodes, etc. Now, you might say that, well, this is actually what eigenvector centrality does, because it's implicitly sort of expands the size of the network that affects you. Well, this is true, but there is one trick here. Leo Katz proposed to use an attenuation factor. So, which means every time you get a next nearest neighbor, the influence of that next nearest neighbor to your centrality actually diminishing. So what he was saying is, this is your nearest neighbors, and they contribute to your centrality measure. Like in the notion of eigenvector centrality. But this guys, of course, has other connections. Was this second tier of nodes, they contribute less to the node importance, and this should be like sort of less disproportionately depends on the distance along the graph to those nodes. So this can be encoded the following way. Remember that if we talk about matrix A, adjacency matrix, every element in this matrix tells us if there is a shortest path between node I and J. Now, if we look at the elements of the matrix A squared, what do those elements tell us?
If a node is connected by at least one hop.
It actually tells you, if A squared, it tells you if there is a connection between the nodes in 2 steps. If there are 2 nodes connected in 2 steps. And in fact, the number, the actual number there tells you how many of those 2-step paths exist in the network. And elements of A cubed tells you if the 2 nodes connected through 3 hops and how many of those exist. All right. So what we can do is we can define the centrality metric as the sum of those metrics, right? So we say, okay, nodes are connected Aij, and we'll put a weight beta on it. Now, if the nodes are connected through the intermediate nodes so you can reach node I, from node I you can reach node J in 2 steps, that encoded in A squared matrix, but we'll put sort of damping factor B squared, and B is less than 1, and so this will be sort of less influence, and 3 steps even less influence, etc., etc. So in some sense, it's tuning up the regular eigenvector model by just saying, look, we take into account the neighbors and nearest neighbors and next nearest neighbors, but we need to make sure that because they're further away, their influence is less. Now, if we write that formula, write it in the matrix notation, that's what we get. And E is a unit vector, is a column unit vector. And when you multiply a matrix by this vector, it just adds the rows, the values in the rows of this matrix. So it is, in matrix notation, it plays the same role as the summation in here, right? Instead of just summing over all J, we can multiply by unit vector, because then what happens, by the definition of multiplication, matrix times a vector, what happens is we multiply every element in the row by every element in the vector. Now, if all the elements in the vector are equal to 1, this is equivalent to just summing all the elements in the row of the matrix. So because of that, this and these are identical. But now it's clear, I mean, at least in this notation, that you can put this together, of course, as a sum, right? It's just this series. And then you can easily, you can show that this sum can be actually written as this inverse. Now, why is it so? If you, for example, forget that A is a matrix, why can't we use this infinite sum and write it as a sort of inverse of something? Does it remind you about any formulas you've seen? Have you seen this? What is that equal to? Do you remember?
Yes, we do.
1 plus x squared, etc. Right? It's a Taylor series expansion. So in fact, you can do similar things with matrices. Just you need to be aware that when you're talking about 1 over matrix, it's actually matrix inverse. All right. So that's why this series can be written as just inverse operator on this on the difference I minus beta a. And again, this is beta a just because of literally this expression. Now, the more accurate way to show this and to prove this, of course, not to divide by matrix, but you can take this equation. You can take this equation and multiply both left side and right side by the value I minus BA, and then see how things will cancel out, how matrices will cancel out. Try this if you never done this before. So, but the point is, by using this trick, we can show how to calculate K. Now, in practice, doing this sort of matrix inverse is not a good idea. So what instead we do is we'll take right now this expression and move it to the left, and so we'll get the following equation. So Katz centrality is given by this equation, with beta being a parameter. It is in the equation, and beta is a parameter in this equation. And of course, beta will control the values of K. Now, if, for example, we set up beta equal to 1, then we'll get sort of regular eigenvector centrality. So it is extension of that metric. If you guys have some questions about this derivation, please at home take a look at it, because we'll be using a lot of this kind of tricks or methods when we start talking about PageRank next time. All right. So, but again, the whole point of this Katz centrality is that, well, let's add some attenuation parameter, and let's sort of diminish the value of the longer connections. So they're still important, but they're not as important as direct neighborhood, and that will change, of course, the metric. There are many more metrics has been derived since then. One more popular metric that I just want to point out is called Bonacich centrality. This is sort of two-parametric centrality measure, though in fact one of those parameters usually cancels out. I mean, it's not canceled, I'm sorry. It's being used to normalize things, and so you do not set up it. The idea here is that in the original formulation of the things, in the original formulation, we always thought about power as being positive, something that is enhancing. Well, the question is, and in particular, Bonacich, he studied the trade networks, and the question he was asking, like, okay, what happens to you if you're connected not to this, when you connect it to a node that is sort of weaker in terms of the power. So if you think about this, different nodes have different powers. Now, if the connection to the weaker node will actually decrease your power, not increase by the value of the power of that node, but actually sort of decrease it. I mean, the idea would be, okay, well, it's like, I don't know, in college, that if your friends getting really bad grades, they also affect you in a sense. You start getting bad grades too, right? So it's sort of bad influence, right? So we can have good influence, we can have bad influence, and the idea of his metric was to take into account that the influence can be good influence or can be bad influence, and so the parameter beta in his approach can be positive or can be negative. And he defined centrality measure the following way. So again, it is very similar. It's sort of extension of regular eigenvector centrality. But if you think about this, okay, well, we can take alpha equal to 0, beta equal to 1. That is traditional eigenvector centrality. We can take alpha to 0 and then use beta positive. It reminds you about the previous slide, the Katz centrality. But here the trick is that the beta can be negative or can be positive. Okay, so we can rewrite this equation the same way. We can rewrite this equation in the matrix notation, and to do that, we're actually doing exactly the same trick as we've done before, where if there is just a summation over the matrix, we replace it by the multiplication by unit vector. And we do not need to add unit vector here because there is already a multiplication here by the vector. So as a result, we get the following formula. And again, it can be rewritten, and we can have a sort of final definition for Bonacich centrality. Is given the following way: alpha beta parameters. And quite often, if you notice, alpha here now sits outside, and so one can use it to, for example, normalize the total value of the parameters, the total value of the centrality. Now, sometimes this metric is called also alpha centrality, Bonacich centrality. And these are sort of the notion here is that beta as a parameter can be quite important in determining the centrality measures. So the Katz and Bonacich centrality, they both use parameters, and that means depending on the choice of the parameter, you can get different values of centrality, and it will sort of emphasize or select sort of different nodes to be more central. And so if you try to use those metrics, you have to be careful, and you have to have some ideas or some explanations why particular nodes or why you choose particular sets of parameters. Now, these guys were coming from psychological, sociological ideas. So here is actually a great picture from Wikipedia. This is a very simple planar geometric graph. And A, B, C, D, E, F, these are different centralities. And in fact, we today talked about, well, pretty much about all of them, right? So we know degree centrality, and this is the degree centrality. And if you notice, there are nodes, and it's color-coded, of course. So the higher the centrality value, the redder is the node. And you notice that here we have nodes with high centrality. Let me use some color that's not there on the palette. Doesn't want to switch. Okay, so there are nodes here and there that have high degrees, but again, this is sort of geometric graph. It's built such a way that there are no nodes with very high degrees, and so we don't have very bright pictures here in terms of centrality. Now, closeness centrality is shown here, and well, it makes sense because the nodes in the geometric center of the graph they are highlighted in red. They're their closeness. Betweenness centrality, these are nodes that act as bridges here in between pieces of the graph. They're not as explicit bridges as we've seen before, but they're bridges, right? And they highlighted. So eigenvector centrality is this reinforced centrality, and there is a group of nodes all together that together sort of the largest cluster and the nodes within that cluster that get the highest values. And then there is this Katz centrality and alpha centrality. Actually, I do not know what parameters, what were the values of the parameters to set them up, but you can notice that in the case of Katz centrality, it does also select this region, which was similar to eigenvector centrality, but it also picks up some other nodes around that has been picked up by this metric, by degree centrality. And alpha centrality, it focuses strongly here on the sort of the core of what we've seen on eigenvector centrality. So these are sort of different metrics, and this is how they allow you to highlight or select different nodes and the roles those nodes play in the graph. Again, just keep in mind that though this is geometric network, very simple planar graph. Well, it's not planar, exactly planar, but close to planar graph. And in real networks, you're going to be dealing with the nodes have power law distribution, right? And so there are a few nodes with very high degree, and there are a lot of nodes with low degree, and there's a connectivity pattern, et cetera, et cetera. And so you might expect that the values of degree centrality, at least, and of many other centrality metrics, they are also have a power law distribution, which means there will be few nodes with very high values of those metrics, and lots and lots of nodes with low values for those metrics. And so you can actually think about doing histograms on those metrics, and they also have to be then in log-log scale to be able to see things in there. Okay. By the way, take a look at the Wikipedia page on centrality. There might be they might have numbers for Katz and alpha centrality for this image. Now, a couple more sort of comments to wrap up the story on centrality. Centrality is defined for the node, right? But it's very clear that some graphs will have a sort of structure that emphasizes centrality, like like a star graph. It's not only that there is one node that has very high centrality, it's also other nodes has very low centrality. So there is something in the structure of the entire graph that we can use to characterize the graph. Or this simple sort of circle where, again, every node is sort of plays equivalent role. It also tells you not only about the nodes, but it tells you about in general the structure of the graph. So one can use this notion of the centralization, which is a graph or network measure. And the idea is the following. You can calculate the centrality for every node in the graph, okay? And then you can select a node that has the largest centrality and calculate the difference in between the centrality of every node and the centrality of that node. And after that, you normalize this, again, because you want to have metric that allows you to compare between different graphs, you normalize to the maximum possible value. And the maximum possible value will be achieved for the star network. So pretty much what it says, okay, well, let's take a star network. We'll build a star network with the same number of nodes as your graph. We calculate, it's clear that the central node in the star network has the largest value. So calculate this max and then normalize respect to it. So this is one of the ways to measure centralization of the network. And you can use actually any metric here any centrality metric to actually measure the centralization. Now, if you look at this, it does remind you a little bit about like normalized variance, just without squares. In fact, you can use that. You can use sort of the variance and the distribution for the centrality measures of the graph. Again, just you have to keep in mind that a lot of those networks we're dealing with are power law distributed networks, and remember that sometimes the mean is, for example, the average is not a good representation. You might want to look at the median instead of mean, right? And the variance can be huge because, again, it's power law. So comparing network one against each other is actually quite complicated. Centralization works really nice and well for sort of small organizational networks, not that nice and well for huge networks. Okay, couple more words. That's this topic. We'll talk more about this next time. But just a couple of words today about the directed graphs. So we started by the story that we'll deal only with undirected network, and that means we use centrality. And I mentioned that sort of traditionally, people in sociology, when they're dealing with directed graphs, they would talk instead about the prestige of the node. And in the sense that the node is, say, prestigious if there are a lot of nodes, if there are nodes pointing to it, or like this one is actually the prestigious node, right? There are a lot of incoming links, and prestigious is not a symmetric measure, right? So if somebody gives you prestige, it doesn't matter, it's sort of it goes back, or think about again nodes as in scientific papers and edges as citations. So a paper is important or prestigious in the field if there has a lot of citations, and sort of equivalently with the metrics we talked about, you can introduce degree prestige, and again, since here it's only incoming links that are important, well, it's K in, which is degree, so based on incoming links. So you're just adding up those counting only incoming links, not just the total degree of the node. You can also introduce what's called proximity prestige, which is similar to the notion of the closeness centrality. But there is a difference, there's a subtle difference, that when we have a directed graph, and directed graph is sort of one-way street, there is, not all nodes can reach every other node in this graph. So there is an issue of reachability. Like, for example, it's very clear that for the node, say number 5, nobody can reach that node, and so proximity prestige here will be 0. But at the same time, say node number 9 can be reached through node number 2 by pretty much majority of the nodes. So doing those calculations, we have to be careful with the directed, with the fact that the graph is directed, and there is a reachability issues, right? Reachability constraints. In fact, the major contribution of the PageRank algorithm, and we'll talk about it next time, was in the fact that how to handle directed graphs, because just brute forcefully going and doing this, say, Katz or Bonacich centrality or eigenvector centrality on the directed graph might not work. Sometimes it will work, but sometimes will not, and it really depends on strong connectivity of the graph, if the graph is a strongly connected component or not. And most of the times they're not, and so you have to do something about it. But that's the topic for next time. For right now, it's just sort of what I would like you guys to remember from this part is that typically when we talk about directed graph, it's a story about prestige as a metric, and there is this status or rank prestige, and really rank prestige. That's pretty much will be page rank for the node. Okay, so couple more notes here is that we have created different metrics, and the question that is very reasonable to ask is, okay, well, are those metrics correlated, right? So you can for example think of imagining of drawing, say, closeness centrality versus eigenvector centrality, and just plotting all the points that have different centrality. And the question is, well, is eigenvector centrality is the same as closeness centrality? Or, in fact, probably more important, is eigenvector centrality and degree centrality correlated, right? The reason, for that question, well, first of all, can you use this different centralities, for example, if you're using machine learning algorithms as features to predict things, or it's pretty much if they carry the same signal. The other simple reason is, eigenvector is actually quite costly to compute, while degrees are obvious. So in fact, if they're just nicely linearly correlated, why bother? So the measure, the traditional measure for correlation in between two random variables is a Pearson correlation coefficient, and there is sort of nothing new about it. We take two different metrics, x and y. We calculate averages for them, and then that's pretty much it. It's covariance divided by standard deviations, right? And it does show us linear dependence between variables, if it exists, and it measures the linear dependence. But we have to be careful here, because sometimes linear dependence or dependence is not what we're looking for. Think about the following. Think about ranking, because now if we go from if we use and when we use the centrality metrics to rank nodes, we're actually concerned more about ranking than the actual value of the metric. So you can think about it the following way, right? So you have all the nodes in the graph, they have some centrality measure. So what you do then is you sort all the nodes by the centrality measure and you rank them. So if your nodes have centrality measures 0.1, 0.7, 0.3, you can actually sort them and rank them, and this will be node number 1, node number 2, node number 3, right? I can rank them by decreasing value of the metric. And so what I might be concerned more is not in a correlation between the metrics, but in the correlation between ranking. So if one metric gives me the same ranking of the nodes as another metric, if you think carefully, the correlation coefficient and this ranking is not the same is not the same thing. It's not the same thing. Just sort of, for example, think for a sec, two functions, say one linear function and one x squared. Both of them monotonically increasing functions. And if you think about the ranking that each of them will give to your nodes, it will be the same ranking. They will give you the same ordering of the nodes. But if you try to compute correlation between the values of linear function and quadratic function, well, it's not going to be a perfect correlation. Though it's going to be perfect, so the ranking will be identical. So Pearson correlation coefficient will not tell you if the ranking is identical. And that's where this sort of Spearman's rank correlation coefficients, or it's also called Spearman's rho, comes in. And the idea is the following. We can convert row scores into ranks. Well, the way I showed here, right? Just literally by sorting and assigning ranks. And now this little xi's and yi's, they're actually integers. They're ranks. And then you calculate the following value. This really comes from the sort of Pearson correlation, but just for the ranks. And it gives us the sort of the strength, the significance of this monotonic association. So it's very clear here that if say you're comparing ranking by quadratic function and by linear function, right? They're both monotonic, but they give you the same ranking for the nodes. This difference for every node will be 0. So the node that ranked number 1 in monotonic will be ranked number 1. I'm sorry, ranked number 1 in quadratic will be ranked number 1 in linear, and ranked number 2 in quadratic will be ranked number 2 in linear, etc., etc., etc. And so then this coefficient will be equal to 1. And so this is the whole point. You might want to have to compare rankings, and to compare rankings, you might want to have that if the rankings are identical. You want sort of your metric to be equal to 1. So that's sort of one of the ways to deal with it. Now, again, there is nothing wrong using Pearson correlation in comparison if you want to compare the values of the centrality measures. But if you want to compare the actual rankings that you get from the centrality measures, you don't use Pearson, you use this sort of Spearman's correlation coefficient. There is another very popular way to do this comparison, and it's called, the ranking comparison is called Kendall-Tau distance. It's actually used a lot in information retrieval when you compare two rankings. The search engine provides you with two rankings for the pages, and you want to see how different those rankings are. Just think about the search results. You look at the search results from, I don't know, Yandex, and you look from the search results from Google, and let's say, the first 20 search results overlap, is the same search results, but they sorted a little bit differently. So the question is, okay, how do we measure this difference in ordering? And the classical way is this Kendall-Tau rank distance. And in fact, what it calculates is the following. It actually counts the number of pairwise agreements and disagreements between two ranking lists. So it's called concordant pairs, those pairs that have the same ordering, and discordant pairs. And Kendall rank coefficient is defined the following way. If you have n numbers in your ranking, you can calculate how many concordant pairs you have. You can calculate how many discordant pairs you have, and calculate this rank coefficient. So, for example, if we have two rankings, one is A, B, C, D, E, and the second one is slightly different ranking, what you do is we go pairwise, and we look at the number of concordant pairs and discordant pairs. Like, let's say A versus B. Here, it's A comes before B, and A comes before B in this case. So it is a concordant pair. B versus C. So B comes before C in this case, but B comes after C in this case. So this is discordant pair. We're not taking into account when we calculate NC. So AB and AB, this is concordant pair. CD and CD is a concordant pair. DE and DE is a concordant pair, and AE is concordant pair. And there is one more which I missed, which is, what is it? So we did AB. Which one? Okay, okay. So this is the sixth one. So you count those numbers, you count those pairs, and you find the ratio, and that's your metric. So again, if you have the equivalent rankings, then this value will be 1. If it's totally reversed, it's -1. And in fact, there is some algorithm that can allow you to do this pretty efficiently. So that's another way to deal with ranking. And in fact, we probably will use the Kendall-Tau ranking a few times in the future. Okay. So to conclude, we look today at the various metrics of centrality. And there is sort of, we started with very clean and clear definition of the radius and the diameter, and sort of the centrality, the central nodes in the graph that comes from graph theory. And then we moved on to the various definitions and metrics coming from sociology. And sort of we looked at degree centrality, we looked at the closeness centrality, betweenness centrality, and you will see these metrics being used all over the place. We talked about eigenvector centrality, and we talked about the modification of eigenvector centrality, which is called Katz and Bonacich centralities. So these are all kind of centrality measures. Again, today we concentrated on undirected networks. Next time we'll talk about how to actually do ranking on undirected graphs, and that sort of will lead us into the PageRank algorithms and how it's sort of where it comes from and how it is used. But again, for social networks, since a lot of them are undirected, these are the major metrics of centrality. Okay, that's it for today. Do we have any questions?
Yes. Could you please go back to slide 17 or 18, please?
17 or 18, okay.
The one about centralization.
Yeah.
Yes.
What is the maximum in the denominator taken over?
Okay, it's a good question. As far as
of over graphs of the order of the same order as the given graph.
Give me a second.
I'm waiting.
So if we consider a graph of an order n, in denominator the value for all graphs of the same order.
Yes. So the point is, so there are a couple things here. First of all, this P star, right, is the node within your graph that has the highest value for the metric. And so what's done here is, you just find the difference in between the highest and the difference between the value of the node for the node and the highest value in the graph. And this one, okay, and here I have to be careful. I need to double check it. There are a couple ways to define this. One way to define it is to actually compare it against, like we said, before, like against the maximum, the graph with the maximum possible value like this, which would be the start graph. Or you can also normalize it with respect to the maximum value in your own graph. This is a good question. Let me double check regarding this formula. Okay. Any other questions? All right, I'll get back to you with with answer on that one. What exactly they meant here. I just don't want to make up my own centralization metric. All right, well then we're done for today.